everybody. Thank you to the organizer for the invitation to this nice conference. So I will talk about estimation in state space model. So we already had several talks about that topics. Here, maybe the difference is that we will try to, okay, I can show you just that we try to learn the model without any assumption about the shape of the model, so using non-parametric estimate as in the talk of Mark, for instance, but also Q and R from a sequence of observation. So some words about the motivations. We consider some boys' data in the small bay here in Bretagne. So Paris is here, and the boy is here in the sea. And this is a time series of the data. So it's not exactly the data from the boys. Those data are models, output data, but they should be similar to the boys' data. So we are in the like a twin experiment because we have model outputs, and we will suppose that which is available are only the observations. So it means the dot points, and we want to filter the noise from these observations and also reconstruct the data where there are some gaps, because in boys' data you have usually a lot of gaps. And we also suppose that we have some covariates which are plotted here, and there are the depths, which is mainly due to the tide. So we have these oscillations. Some wind data, which are important for the waves, they are here. And some information about the waves offshore. So the buoys is here, and we have also information about the waves from another points offshore. Okay, so waves data are usually recorded with noise, and there are quite a lot of gaps in the time series. So we don't really use directly the waves, but a synthetic a parameter which is linked to the energy of the waves, and it's called HS. It's a significant wave height. More or less, it's a height you will infer if you look at the sea. If you want to make surf, for instance, you look at the sea and you say, okay, today we have 1 meter waves or 2 meter waves, and this parameter is highly related with this height. And here I plotted on the left plot the HS at the buoys with respect to the depths, and you can see that you have some oscillations which are nonlinear. On the second plot, you have HS with respect to the waves offshore, and on the third plot, the HS with respect to the wind. So some of the relationship with the covariates are nonlinear. So if we want to fill the gaps here, the natural idea would be to use the machine learning methods or regression methods and use the covariates and some information of the past of HS and just feed the nonlinear, the machine learning and do the prediction. But we have to take care that the observation noise will affect the results. So let us give a toy example, which is a little bit simpler and where we have no covariates. This is state space models where we suppose that xt has a dynamic which is a sinus. And what we have is an observation of xt, and it is observed with noise. And if we use, okay, what we want to do is to estimate the dynamic, so the dynamic, the sinus from an observation time series. Okay, on the left plot, what we do is that we use a time series of xt, so like a perfect observation without noise, and we try to retrieve the red line from the black dots, with a nonlinear, non-parametric estimation, which is the blue line. Okay, so if you have no noise, the estimation is almost perfect here. And on the left, the right plot, you have some noise on the data, and you can see that you get a biased estimate. You are not able anymore to retrieve the red line. So we say that if we want to use machine learning method to estimate a dynamic or to use it in a data assimilation method, we need to estimate the noise. It may be the observation noise. It may be very important. So to fill the gap in time series, state-based model is a natural framework because it allows to take into account the noise on the observation. So what we propose here is to try to fill gaps, or to reconstruct the state X given the observations and the covariates, and no information about the M. Okay, we just have the observation time series and some observed covariates, and we want to reconstruct X. So the proposed approach is an iterative algorithm with 3 steps. It is very similar to what we saw yesterday and the day before when we use EM algorithm. So the first step is to use a smoothing algorithm to reconstruct here X when M, Q, and R are given. Then we'll use machine learning methods to estimate M given X, the X inferred in the previous steps. And finally, if we have a X, a M, we can estimate Q and R using EM algorithm. So that's just a slide to say that we will use sequential data assimilation, and we'll decide to use a particular filter. So that's for the first step. So for the data assimilation steps, we use a particular filter. For the second step, once we have a time series of X, we need to estimate M. And I said I will use machine learning methods, and I decide to use local linear regressions. In the previous talks, most of the people used analog methods or neural networks. So in my application, I have a small dimension. Okay, so I can use non-parametric estimates like analog methods. And what we found is that usually LLR is better to extrapolate a little bit the prediction. When you are close to the boundaries, you have better estimates. So the idea is just nearest neighbor methods. For a given X, you look for the neighbors, but instead of just computing the mean of the neighbors, you fit a linear model. Okay? So it could be written like this, that M is just approximated by a polynomial of degree G. And if the degree P, if the degree is equal to 0, you just retrieve the nearest neighbor method. And if the degree is equal to 1, you retrieve the LLR. And we use a kernel in order to give more weight to the points which are close to X and less weight to the points which are far away. It leads to such results for the sinus model. So the different plots correspond to different lengths of the learning time series. On the first plot, we have only 100 observations, and on the last plot, we have 1,000 observations. Here, as you can see here in the equation, we suppose that the observation is perfect, so there is no noise on the observation, and we just want to compare the nearest neighbor method, which is in green, with the LLR, which is in blue, just to check if the LLR is better or not, because it is a little bit more costly, so it has to be better. So here again, the red line is the truth. The green line is for the nearest neighbor methods and the blue line for the LLR. And you can see that if the catalog, the time series we use to learn is big, there is no difference between both estimates. But if the length decrease, you can have quite a huge difference between the nearest neighbors methods and the LLR. So for the forecasting, we use LLR. So in fact, what's happened is exactly the same what Mark done or Manuel too, is for the forecasting step, instead of using a true M, a true model, we use an approximation of the model, and the approximation is given by the LLR. So in fact, what we do is that we have a catalog, a learning time series. In the learning time series, we look for the nearest neighbors, and then we look at the successor of the nearest neighbors, and we just fit linear regressions given the successor. So what's happened if we do that? Again, the results here in the table are for the sinus model. We can compare what the forecast error. So in the forecast error, you have just information about M. With smoothing error, in the smoothing error, you have information about M, Q, and R. But in these results, we have Q and R are known. And you see that if you forecast or if you do the data simulation with the estimator of M instead of M, you have about the same results. Okay, if the observation is perfect. So now we have checked that the non-parametric estimate is seems to be good. So if we now we have to learn, if we are able to learn M, if we have a good catalog, now we have to learn Q and R. The standard method to do that is the one which was presented by Manuel Pulido yesterday, is to use an EM algorithm, more specifically stochastic EM algorithm. It is an iterative algorithm. It starts from chosen value of Q and R, and it will maximize the likelihood of the observations given these parameters. It composes of two steps. In the first step, usually called E steps, the idea is just to get an approximation of the smoothing distribution. So we just generate particles which are time series of the states. Okay, given a smoothing algorithm. So you could use ENKS algorithm or particle smoothing algorithm. And then once you have time series of which are realization of the posterior distribution, you can estimate Q and R using the classical estimates, which you can derive from the likelihood. Okay, you do that if M is known. Okay, but in our case, we don't know M. We have no model for the evolution of the HS. So we derived a similar algorithm, but where M is unknown. And in this case, you have to add some steps, which are written in purple. So the idea is that we will start from the observation, for instance, but the observation is noisy, and we'll try steps to filter the noise, so to remove the noise from the observation. So we start with a chosen value for Q and R, and from a catalog, which is, for instance, the observations. And we'll do the same steps. So in the first steps, given the current catalog, we'll estimate M hat, an estimation of the dynamic operator. And with this M hat and the parameters, current parameters, will generate particles which are realization of the states. Once we have the states, we can estimate Q and R. And then we have to update the catalog given the current parameters. Okay, or Okay, maybe we just not update the catalog, but we have to re-estimate the M with the new catalog. And the new catalog, in fact, is the last version of the smoothing trajectory. So this scheme just sum up what I said. We start with some chosen value of the parameters and an estimation of M, which is obtained from the observations, and then steps to steps will correct the set of observations by filtering the noise in some sense. And here on this plot, you can already see that we start with such a scatter plot on the left, and in the second iteration already you can see that the scatter plot is less broad. And okay. So this is a slightly different plot. It's again for the sinus model. We suppose that at the beginning we have 1,000 observations, and the SEM algorithm has been run with 10 particles and 200 iterations. And in the middle you have the true states we used to do the experiments. On the left, the observations. And again, the red line is the truth, and the blue line is what we estimate from the dots. And on the left, you have the final iteration of our algorithm. So you can see that now the scatter plot or the points are very close to what we had in the states. And the estimation of the dynamic is also quite good because the blue line is very close to the red line. So if we want to have a little bit more information about the quality of the reconstruction and the estimation, so the top on the plots, you have the evolution of the estimation with respect to the iteration, so the abscissa is the iteration. And you can see the estimate of Q, of R, and a plot of the evolution of the likelihood. And for Q and R estimates, you have 3 curves. The black curves is the estimation if you know the true model. Okay. The blue curve corresponds to the estimation if the model M is estimated from a perfect observation. Okay, so if you have no noise on the time series used to estimate M, and the red line corresponds to the last algorithm, but it means the algorithm where you estimate Q, R, and the estimate, and you update your catalog step to step. So you can see you have quite a good agreement between the 3 curves, and in particular the red curves converge to the other one. And in the table we have plotted some root mean square error on the first line for the forecast. So in the forecast, as I said earlier, we take a new time series of the state and we try to forecast with the estimation we obtained from M. And we have also the RMSE between the true state and an estimate states obtained by smoothing. And you have 4 columns. For the first one, you use the true model and the true parameters. So it corresponds to what we want to approximate. On the second column, it's a case where you use observations to estimate the model, but the true parameters for Q and R. And you can see you have a big divergence between the truth and what you do with the noisy observation. Okay? In the third one, you use the true model, but you estimate the covariance error, Q and R. And in the last column, you estimate everything. So you start with the observation. You have only the observations, okay, which is noisy, and from that you estimate the model Q and R. Okay, and you can see that we are not far away from the truth. Okay, and we improve a lot the results compared to a scheme where we would just use a noisy observation. Okay, back to the application. So we run this model on the applications. Once again, I remark that we are the data are not true Boy data, but outputs from models, so we know the truth. So we are able to compute the root mean square error. And here I just recall the model and the covariates and so on. So now the results. In these results, we compare 3 algorithms. One algorithm where we just use Kalman smoothing to estimate everything. So we suppose that everything is linear and we have no covariates. Case where we use ensemble Kalman smoothing, and the case where we use a particular smoother instead of the Kalman ensemble smoothing. So the estimation with the particular smoother is plotted in black. The Kalman ensemble Kalman smoothing is plotted in blue, and the Kalman is plotted in light blue. And we did the experiment with different value of the observation noise. So we increase the observation noise from 0.1 to 0.5. So it corresponds to the 3 columns. And on the left, we just do a plot of the estimation of error with different catalog size. Okay, for the first one, we suppose we have only 1 month of HS observation on a daily time step, and then when we took 2 months and 3 months and 5 months. Okay, and what we see is that all the algorithms quite well estimate error, but the estimation is better with our algorithm, and it is not affected by the catalog size for the error noise. And here we see that when the noise increases, it's more difficult to have a good estimation. It's expected, okay? And what we see also is that with the algorithm we propose, we have a better estimation than with the other algorithm. I have to remark that with the EN case, we didn't update the catalog. So we just use the initial catalog for each iteration. And a final remark is that if we just use the machine learning algorithm, so we just use LLR without any smoothing and any estimations, the error would be, for this case, about 0.15. Okay. So the fact that we estimate the error and we do the smoothing, it helps to really improve the reconstruction. And here to finish that the time series, so I did a zoom on the 10 first days. So the first line is what we do with the Kalman smoothing, then ensemble Kalman smoothing, and then the particular smoothing. The dots as the observations. The black line corresponds to the true time series without observation noise, and the red line is what we reconstruct. And the shaded area corresponds to confidence intervals. Okay, and in Kalman, there is no covariates. That's why we are not able to retrieve the effect of the tide here. It is retrieved in ENKS and CPFBS. Okay, and with the particular filter and update of the catalog, we see that the time series, the red time series, is a little bit smoother and with a thinner confidence intervals. So some concluding remarks. The first remarks is that for missing data imputation, it's very important to take into account the noise in the observations, and that data-driven state space model or data-driven data assimilations is a pertinent framework to do that. Third remark is that with only the observation time series, we are able, using data assimilation combined with machine learning methods, to estimate the states and the both error, the model error and observation error. There are a lot of work to do then. From that one is that we should try to do that with real boy data, which is not so easy because they are usually quite short in that area with really a lot of gaps. Then it would be really interesting to have a version of the algorithms which are efficient also in higher dimensions. And it's not so straightforward because the machine learning algorithm and the particle filter both are sensible to the course of dimensionality. But I guess that the talk we had this week give a lot of ideas to find some response to that. And it could be interesting too to have some theoretical properties of this algorithm. And maybe it's not so difficult because it's these algorithms with the Markov chain. And so we have to check the ergodicity properties of the Markov chain and then to have some information about the asymptotic distribution. Thank you very much.
We have time for a few questions.
Very nice work, thank you.
Thank you.
There is some diurnal periodicity, right, in these data.
Yeah.
I don't know whether you're aware of a method that we developed for, well, gap filling, which is what you call imputation in statistical parlance.
Yeah.
In the presence of periodicities, and there's a paper that has gap filling in the title, and my name and the one of Dmitry Kondrashov, who couldn't be here. It would be interesting, especially in higher dimensional cases,
Okay.
to compare.
Okay, thanks for the remark.
Just curious, but maybe I didn't get all of the point. But in the final algorithm, one in which you try to estimate the dynamic itself, so what you call M@, and the noise Q, I was a bit curious, but there is not, I mean, those two elements are not unique. So if you only have the sequence of your data, which are noisy, then the combination of those two, so how big Q is and how the dynamic M@ is not unique. I mean, you can have a different combination of them.
Probably you have some local maxima when you.
No, but,
Okay, you
I mean,
think
in
it's
the
not
case-
unique? Maybe.
No, go ahead. I'm sorry. Go ahead.
Not sure. Yeah, but maybe it's not unique. Yeah.
Because I think in the case when you make a twin experiment, okay, you can talk about it is converged to that, but in a anyway, okay.
I understand your question, but I am thinking about it. Yes, it converges to a local maxima. I can just do that, and okay, maybe you could find other couples which reply to this, which allow to do the same reconstruction. This way to mine. Yeah, we didn't. Okay. We tried different initializations, and each time it's converged to similar solutions. But okay, maybe with very different initial conditions, it could converge to something else. And it is also a point which has to be checked in the theoretical study.
I think this is about time where we should stop. So let's thank Valérie once again.